Okay, momentum is a measure of how hard it is for an object to stop moving once it's already in motion. All right, so momentum is related to both the mass of the object and the velocity or speed that the object is traveling at. All right, so all moving objects possess momentum. All right, so the equation to calculate momentum, momentum is denoted by the lowercase letter p, all right, and it's equal to the mass times the velocity. All right, so momentum is not denoted by m, which you would think it would be, but m is already taken by mass. So they tried to use a different letter of the alphabet to um, use for momentum. All right, so momentum is P is equal to mass times velocity, and it is a vector. Okay, so velocity we know has magnitude and direction, so does momentum. All right, so the direction of the momentum vector is the same as the direction of the velocity vector. So whatever the direction of the speed of the object, that's going to be the same direction that the momentum is going to be in as well. All right, impulse is denoted by capital letter I, and it's the product of an external force and the passage of time. All right, so this is the result of a change in momentum. All right, so impulse is equal to force. Don't forget, force is simply a push or pull on an object, and then the passage of time. All right, so the force multiplied times the passage of time is equal to the change in momentum. All right, so the SI unit for impulse is going to be force, which is newtons, times time, which is in seconds. So impulse is newtons times seconds, or our momentum, which is mass, which is in kilograms, times velocity, which is meters over seconds, right? So either or for impulse, but you usually see it as force times time, so newtons times seconds. All right. So here, the area under the curve is the impulse. You have a force in newtons along the y-axis. All right, so this is the positive y-axis. And then you have time in seconds along the positive x-axis. So under that curve here is your impulse. So newtons times seconds. The law of conservation of momentum simply states that the resultant external force on a system is zero. All right, if this is true, then the vector sum of the momentum of the objects will remain constant. So this means that the initial momentum is going to be equal to the final momentum, right? Conservation just means same. All right, we will also be discussing collisions here in chapter 6. Collisions between objects are governed by Newton's laws. All right, more specifically, Newton's third law of motion, where every action is met with an equal and opposite reaction. So again, Newton's third law, it tells us that the force exerted on body A on by body A on body B is a collision, and it's equal and opposite to the force exerted on body B by body B on body A. So pretty much for every action, there is an equal and opposite reaction. So that's Newton's third law of motion, and it pertains to collisions between objects. So if you have more than one object and they bump into each other, that's what a collision is. All right, two objects that are bumping into each other. All right, so let's say we have two objects here. Let's just say they're tennis balls or something like that. All right, you have the force of gravity in the downward direction towards the Earth's surface, Once they collide, you'll have the force in the opposite direction of the collision, and then you have the normal force of the ball on the ground. All right, so during a collision, your external forces are ignored, and the time frame between that collision is very, very short. So the forces are impulsive forces. So it's a high force over a short amount of time. All right, so it has a short duration. All right, so these are the collision types. There are three. All right, there's elastic collision, there's inelastic collision, and then there is perfectly inelastic collision. All right, so during an elastic collision, that means that the initial objects remain the same amount of hardness as before the collision. So there's no change in shape to the objects. So let's say two basketballs bounce against each other. All right, the basketballs are not going to deflate just because it hits another ball. Okay, so they kept their shape. No deformation just means no change in shape of the original object. All right, so P, which is our momentum, that is conserved, and then the kinetic energy is conserved as well. So again, kinetic energy is the energy of motion. All right, the equation for kinetic energy is 1/2 mass times velocity squared. And I told you guys, you only square the velocity and not the entire equation, or you will get it wrong. All right, next we have inelastic collisions. This is when you have deformation. So again, deformation means change in shape. All right, so this means after two objects collide, they actually change the shape. They're not the original shape that they were that they started out originally. All right, so in a inelastic collision, we have momentum, it's conserved, but the kinetic energy is not conserved. All right, so the motion kind of stops after the collision. So let's say we have two eggs, and both of these eggs just kind of collide into each other. And it's strong enough of a force to break the shell of the egg. So we can't put that shell just automatically back together again. It's broken. All right. The yolk and everything is spilling out. Right. So there is a change in shape. So deformation means change in shape. All right. Inelastic collision, um, it loses its original shape of the object. And then last but not least is perfectly inelastic collision. This is where you have two objects that collide and they stick together. All right. Um, so in this perfectly inelastic collision, we have momentum that is conserved and the kinetic energy is not conserved. So similar to inelastic, except after the collision, um, the items kind of just stick together. They're stuck together. Right? So an example of a perfectly inelastic collision would be two cars crashing into each other, right? The metal parts of the vehicle kind of stick together. And sometimes you have to have, um, some sort of um, trailer or something like that to pull them apart to help, separate those vehicles that have been mangled together. All right, so those are your types of collisions. All right, so again, for your inelastic collisions, only momentum is conserved. The kinetic energy is not conserved. So you're going to have some change in shape. All right, so some deformation will occur from those objects that collide. And in perfectly inelastic collisions, this is when you have those objects that are stuck together. All right, so they stick to each other. So again, examples are automobile crashes, catching a ball, and the recoil of a gun. All right, so this is a example of a perfectly inelastic collision. So we have a grandparent kind of skating a little bit faster than a grandchild. So she just kind of picks them up, scoops them up, and they skate off together. All right. So she, let me start from the beginning. She weighs about, well, not weighs, but her mass is 80 kilograms. This is the grandma. And she is going to inelastically collide with her 40-kilogram grandson here. He's at rest. So this is why she is able to catch up to him, pick him up, and continue skating, because that momentum is still there. All right, so what we're trying to find out is what is their velocity after the collision. All right, so let's write down our knowns and unknowns. We know that the mass of the grandma, let's call her M1, she was 80 kilograms. And her speed, let's call that V1, was 6 meters per second. All right, the grandchild, let's call him mass 2. He was 40 kilograms and his initial speed was at rest. So he was going 0 meters per second. All right, so what was he, 40 kilograms? Yep, 40 kilograms. And his initial velocity, so let's do V1 initial here. And then do V2I here for the kid, V2 initial. They told us he was at rest, so that was 0 meters per second. All right, so if we go back into the slides, we will see that our conservation of momentum law says that the momentum, the initial momentum, is going to be equal to the final momentum. All right, and momentum itself is mass times velocity. All right, so that's going to be our conservation of momentum equation. So conservation of momentum equation. Okay, so it's going to be our initial is equal to our final momentum. All right, and momentum itself is mass times the velocity. So you're going to have M1 V1 initial plus, okay, so we have 2 people, so we need to do it twice. So we're going to have M2 times V2 initial. So this is the grandkid. And that's going to be equal to our mass times the velocity final. So let's put V1 final. Go back. V1 final plus M2, this is for the grandchild, M2 V2 final. All right, so what we're trying to find is our final velocity. All right, once they collide into each other, what was the final velocity? All right, so the final velocities are on this side of the equation. So we want to put V1 and V2 together since they are colliding together. All right, so we're going to copy down everything for the left-hand side, but we need to factor out our final velocity on the right-hand side of this equation. Right, so M1 V1 initial plus M2 V2 initial is equal to, and let's factor out these final velocities. Let's just call it V final. All right, since they're colliding together, we don't need to separate them into 1 and 2. Let's just do it all in one swoop. All right, so factor that out. If you take out V final, you'll have the mass of the grandma plus the mass of the grandchild. All right, so to solve for V final, because that's the unknown variable that we need to solve for, all right, we need to move M1 plus M2 to the other side of the equation, and we can do that by dividing by M1 plus M2 on both sides. What you do to one side of the equation, you have to do to the other. So M1 plus M2. All right, so this M1 plus M2 cancels out right here on this side of the equation, and you end up with V final being equal to the mass of the grandma times the velocity of the grandma initially, plus the mass of the grandson times the velocity of the grandson initially, divided by their masses in the denominator. So let's go ahead and plug all of this in. So let's come down here. V final is equal to, all right, let's start plugging everything in. Mass of the grandma is 80 kilograms. And we're multiplying that times her velocity, which was 6 meters per second. All right, now we're going to add that to the mass and velocity of the grandson. So his mass was 40 kilograms. And his velocity at first was 0 meters per second. So anything times 0 is just 0. Right, so this second part right here is 0. And then that's divided by their masses added together. So in the denominator, you're going to have 80 kilograms plus 40 kilograms. It is 4 meters per second. All right, so the kilograms in the denominator are going to cancel with the kilograms in the numerator. So the only thing you're going to have left is meters per second. All right, so 4 meters per second. Now this is kind of confusing because I know there's a lot of M1, M2, V1, V2, final, initial, right? It can be a lot. So if you feel like you just, may not be able to work it out fully, at the top of the problem that we did, they already solved for V final for you. So what I did was I started from the jump and then solved for V final. But here, they kind of already gave it to you at the top of the problem. Initial is the before stage information, and then the final is the after the collision information. So their masses didn't change. So technically, we didn't really need to put initial and final for the masses because they didn't lose weight while they were doing this exercise. So masses are the same. The only thing that changed was their velocity because they collided together. So the first set of information that I gave you, this was for the grandma. So her weight, which is M1, and then her velocity was the 6 meters per second. And then the second set of information, it was the kid, was her grandkid. All right, so we added the grandma information. So grandma plus the kid. And this is initially before the collision. And then on the right-hand side of the collision, so this is after collision. And this is the grandma plus the kid. All right, so final is after the collision, initial is before the collision. So initial is on the left-hand side of the equation, final is on the right-hand side of the equation. We factored out the final velocity because we no longer need to split them into the grandma and into the kid. because what they did was when they collided together while they were skating, they're stuck together. So technically, they're both going to be moving at the same speed. You don't need to separate V1 and V2. All right, it's just going to be the final velocity is going to be the same for both. So that's how I factored out the V final on the right hand side of the equation. This is probably one of those areas in physics where people probably kind of get the most confused because there's too many small subscripts here, and you can kind of lose sight of what the equation is even talking about. Okay, we got a couple more slides to go. All right. All right, so next up is explosions and recoil, which we definitely won't be dealing with any explosions and recoil, but this is just for your information. So when you have an object and it separates suddenly, this is the reverse of a perfectly inelastic collision. So math-wise, it's handled like an inelastic collision. All right, so your momentum is conserved, your kinetic energy is not. All right, so examples of explosions and recoils, these will be, cannons, guns, radioactive decay, so forth and so on. So for your elastic collisions, again, momentum and kinetic energy are conserved. So again, elastic collision, this is when the objects bump into each other and they don't change shape, they don't stick together, they're still their own individual objects. All right, so two basketballs bumping into each other, two tennis balls bumping into each other, they remain in their same shape. All right, so there's no deformation, so the shape doesn't change. And again, examples are your pool balls when you're playing pool and the balls bump into each other. The balls aren't breaking when they bump into each other, right? They stay the same shape after the collision. Marbles are also a good example, particle collisions as well. And I think that was the end. Yes. So that's the end of chapter 6 on momentum. And another, you know, example of momentum, like if you've ever watched a basketball game, and well, especially before COVID-19, when you have a player trying to, run very quickly down to that team's basketball goal to put the ball in, but they're not able to stop themselves because they're running so fast. So sometimes they used to run into the audience on accident, or they, run past the basketball goal because their momentum was just too fast for them to slow down. Right. So again, momentum is how hard it is to stop a moving object.